மேடம் 23 இருக்கு.
23 ஜூன் இருக்குதுப்பா. பழசு பண்றீங்க. சிவசங்கரி மேம்
மாத்துறாங்க நினைக்கிறேன் மேம்.
போடுங்கம்மா.
ஐயோ சார், அது மாத்து.
அதுக்குன்னு இப்படியா?
Shiva ma'am.
Shiva ma'am, please stop sharing your screen, pa. Shiva Shankari ma'am.
Shiva.
Somebody call her and inform.
Yes ma'am, yes ma'am.
நான் தான் இன்ஃபார்ம் பண்ணேன்.
Hello. Good evening, ma'am.
Good evening, ma'am.
Good evening, ma'am. Ma'am, mute la இருக்கீங்க ma'am.
Good evening, ma. Good
Good
evening.
evening.
Late ஆயிடுச்சோ சார் ஜாயின் பண்ணிட்டாரா?
மேம் இப்போ ஃபோன் பண்ண மேம் 1 minute ஜாயின் பண்ணிடுறேன்னு சொன்னாரு மேம்.
ஃபைன் கேட்றேன்.
Good evening, ma'am.
Good evening.
Good evening, madam.
Good evening, sir. Good evening, sir.
இந்த லெஃப்ட் சைடுல இருக்கிற அந்த டேபை க்ளோஸ் பண்ணுங்க பார்க்கலாம்.
நானா?
சிவசங்கரி
மேடம். அந்த ஸ்லைடு ஃபுல் ஸ்கிரீன் எடுத்துக்குவாங்க.
பேசிக் சயின்ஸ் மேத்தமேட்டிக்ஸ் இருக்கிறத க்ளோஸ் பண்ணுங்க.
Update.
ஐயோ சாரி மேம்.
சிவசங்கரி அவருக்கு ஜாயின் அவருக்கு ஏதாவது டிஃபிகல்ட்டி இருக்குதான்னு செக் பண்ணிக்கோங்க.
ஓகே மேம் இதோ பார்க்குறேன். மேம் ஜாயின் பண்ணிட்டு இருக்காரு மேம். வந்துருச்சுன்னு சொன்னேன்.
யூடியூப்ல எத்தனை ஸ்டூடெண்ட்ஸ் ஜாயின் பண்ணிருக்காங்கன்னு செக் பண்ணிக்கோங்க. Counselors, please follow up.
Ma'am, 71 as of now.
Totally, it should be 700, right? Including the faculty, it should be more than 720.
Ma'am, sir join பண்ணிட்டாங்களா?
இல்லையே.
சிவசங்கரி மேம் 4-5 ஆயிடுச்சு அடுத்தது.
மேம் மேம் சார் வந்துட்டாரா பாருங்க, கனெக்ட் ஆயிடுச்சுங்கிறாரு.
என்ன நேம்ல இருக்காங்க?
சார் எந்த நேம்ல இருக்கீங்க சார்?
சுசீந்திரன் இருக்கிறது சாரா? ஹலோ சார்.
மேம் அவரோட நேம்லயே ஜாயின் பண்ணிருக்காங்க மேம். ப்ரொஃபசர் இருக்குங்க மேம்.
அந்த இருக்காரு.
இருக்காரு. he is there.
சார் இருக்கீங்க சார்.
அன்மியூட் பண்ணனும் சார்.
போனுக்காக மியூட்ல இருக்காரு. சார் எஸ் சார், எஸ் சார், கேக்குதுங்க சார்.
ஓகே, இப்போ லோட் பண்ணல.
சிவசங்கரி மேம், you can stop sharing.
இது காணோம். லோட் அப்லோட் பண்றது, என்னோட ஸ்லைடு அப்லோட் பண்றதுக்கு.
ஷேர் ஸ்கிரீன் சார். சிவசங்கரி நீங்க ஸ்டாப் ஷேர் பண்ணனும்.
நான் ஸ்டாப் பண்ணிடுறேன். எஸ் மேம்.
You want to continue? Yes.
தண்ணி
Share ஆயிடுச்சுன்னு நினைக்கிறேன். Should be
Yes,
visible.
sir.
Visible now?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
நான் பேசுறது கேக்குதா?
Yes, sir.
Is audible?
Yes, sir.
Oh, fine.
Yes,
Very
sir.
good.
Yes,
Your
sir.
screen is visible and you're also audible, sir.
கேக்குது sir. Yes.
Start பண்ணிக்கலாமா?
Yes, yes.
Yes, madam.
Yes, ma'am.
பண்ணிக்கோங்க. Counselors, you please follow up the other students so that they are joining. Okay, in 3-4 minutes, let them also join. Start பண்ணிக்கோங்க.
Yes, ma'am. A very pleasant evening to one and all present here. Mathematics is gate and key to science, also the mother of engineering. With great honor and privilege, on behalf of management, institution, and Department of Science and Humanities, we welcome you all. We welcome you all for this webinar on Why Mathematics for Engineers by Dr. V. Tangaraj. Positive action combined with positive thinking results in great success. I take pleasure to invite our beloved HOD, Science and Humanities, Dr. S. Pavai Madheshwari, to welcome the gathering.
Thank you. Thank you, Lalita. Beloved Professor Tangaraj sir, my dear fellow faculty members, and my dear students. A very pleasant and happy evening to every one of you. Today, we are gathered here to listen to Professor V. Tangaraj, who is an eminent mathematician, topic, why mathematics for is a question in many of your minds.
My voice break ஆகுது.
Ma'am, your voice is
Voice
breaking.
breaking, sir.
Yes, ma'am.
இல்ல, நீங்க பேசுறது break ஆகுது.
Okay. You please give 1 minute. Okay, I will change. One minute. Now is it okay?
Yeah.
Sorry for
The voice audible?
Yes, sir.
Okay, fine.
Sorry for the inconveniences caused. Okay. So this is a question, why mathematics for engineers? This is a question in many of your minds, right? See, many people, they have developed a sort of fear with mathematics from their younger age. When I am introduced as doctorate in mathematics or teaching mathematics in an engineering institution, in any crowd, in any function, marriages, to some of my relatives or friends, they will show some reactions like, oh, I can't even stand near you. I will keep 1 feet distance from you. Mathematics was a nightmare for me when I was doing my engineering or even schooling. But it is not that difficult or a dry subject. If you learn with patience and understand the concept, then it is a beautiful subject. The beauty is, whoever is doing the problem and whatever technique they are using, the answer will be the same. Different approaches, but all will lead to the same answer, of course, if done correctly. Also, The complete nature is governed by certain concepts of mathematics. If you observe, you can relate and enjoy the beauty of the nature and the beauty of mathematics. The very simple example for admiring the beauty of mathematics is the golden ratio, phi, the number 1.618. Just Google it and see how this number is related to the beauty of the nature, the galaxy, the flowers, the arrangements in the fruits, etc. How it is related to the world's wonderful buildings, drawings, or paintings. Just Google it and see. Just type golden ratio and you can get enough number of pages you can refer to. Not only in the existence, mathematics is the base for any knowledge that we are gaining, particularly in engineering and technology. To elaborate on this, of course, to convince you that mathematics is beautiful and it is essential for your career, we have Professor Thangaraj, who is the most suitable person for this task, here with us today. I welcome you, sir, for this webinar on why mathematics for engineers. I take this opportunity to thank you for accepting our invitation and being the resource person for today's webinar. I sincerely appreciate the IQAC team and our faculty members of our department for organizing such a wonderful event for the benefit of our students. I extend my warm welcome to my fellow faculty members and my dear students. Okay, again, the same request to my dear students. Please listen to this. Try to understand what sir is telling you. Okay, take that into your mind and then you try to explore on that. Okay, so with this note, I welcome one and all again for this wonderful webinar. Thank you for the opportunity.
Thank you, ma'am, for briefing us the significance of this program. Self-belief and hard work will always earn you success. I am privileged to invite Mr. Vijay Kumar, Division Head of Mathematics Department, to introduce our chief guest and the resource person. Sir, please.
Thank you, madam. Sir, good evening, sir.
Good evening.
Good evening to one and all present here. This is Mr. Vijay Kumar, Associate Professor in Department of Science and Humanities, Mathematics Division, also Branch Coordinator of EEE and E&A Department. I feel privileged to introduce an eminent person, Dr. V. Thangaraj, an independent researcher. Our speaker for today's program is having a very deep knowledge in mathematics. He is a very eminent academician as well as an administrator. He retired as director at Head Ramanujan Institute for Advanced Study in Mathematics and director in charge Institute of Distance Education, University of Madras. And later worked as Controller of Examinations, Veltech Rangarajan, Dr. Sakunthala R&D Institute of Science and Technology, Avadi, Chennai 62. Professor Thangaraj was awarded doctorate degree from Annamalai University in the year 1983. He has 33 years of teaching experience and 43 years of research experience. Sir area is probability and theory and stochastic process. He produced 12 PhD scholars and 48 MPhil students. He has published and presented many journal papers, both in national and international. He assisted as editor in many books, and one of the book named Mathematical Vocabulary in Tamil was funded by Government of Tamil Nadu. He has organized around 22 programs like seminars, workshops, and conference, and also acted as a member of several inspection committees for various post affiliations and college affiliation. Sir has carried out many consultancies works and community services. He received many appreciations in this regard. Thank you all for this wonderful opportunity. Thank you.
Thank you, sir. A man of distinct vision and a fountainhead of illuminating ideas, an idol of knowledge, experience, and inspiration. I am profusely elated to invite our eminent speaker to kindly take over the session.
Hello, I'm audible.
Yes, sir.
Yes, sir.
Yeah. Thank you very much for inviting me to share some of the ideas of mathematics among the young minds. This is a very nice arrangement, and though it is postponed due to pandemic period and also other academic programs, and now at least now I could share some of the ideas about how this mathematics is used in engineering. And this now people are thinking mathematics and physics can be removed from engineering. It leads to say, if you have a fingers without nail, what is the use of it? You cannot hold anything. So mathematics will be a tool and a supporter and a part and parcel of engineering sciences. This is a usual request. What is mathematics, first of all? It is an expression of the human mind that reflects active will, contemplative reasons, and the desire for aesthetic perfection. You can see that in Courant and Robbins' book. And mathematics can be thought of as fun, like Sudoku. I think solving Sudoku is a challenge to the young minds, and you have to sit and concentrate on it, and you have to fill up this 9 by 9 square with the numbers from 1 to 9. Each 3 by 3 square will be occupied by 1 to 9. Like that, all the other small 3 by 3 squares. I think everybody knows very well about it. What is the use of this? This is a fun, and also at the same time, it will refresh your brain, rather polish your brain to think about it in a new way. There are so many Sudoku puzzles. Can you write it in English? Blah, 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 960. Sudoku puzzles are available. And is there a puzzle with 16 sorting entries? It's an open question. If anybody finds a puzzle with the 16 entries, you can share and among your friends and then try to solve it. In fact, this is 9 by 9. I have solved it by 4 by 4. That means 16 by 16. That is a very big one. I could do it in 1 hour. 1 hour is the least time. That's what the people say. So you have to spend and a very intelligent way how to fill up all the squares. Mathematics is challenging, like climbing Himalayas. Recently, you might have heard about the proof of Riemann's hypothesis, and one has to verify it. People are verifying the proofs given by our Indian professor. Actually, he is a physics professor working in Hyderabad, one technical institute, Srinidhi Technical Institute, I think. So this Riemann hypothesis It is all started with counting process. In those days, how to count the sheep, flock of sheep, only using pebbles. They have counted number of sheep in a flock of sheep. And then that is why the name calculus comes. Calculus in Latin, calculation means pebbles. So in that process, when you define anything, for example, you have a natural numbers, and then you have integers, and then from the integers, you are defining a prime integer and a composite integer. The question arises, how many primes are there? And then Euclid himself given a proof that there are infinitely many primes. Okay, fine. But next question is, up to certain point, x, how many primes are there? That is a very standard question in number theory. And then people try to solve this. This is called prime number theorem in number theory. In the course of giving a proof, Riemann has worked only one paper on the number theory, and this is he was trying to give a proof for prime number theorem. And in the course of the proof, he is defining a function called zis. There is nothing but a summation n going from 1 to infinity 1 by n power s. It has a real part half. I mean, or zeros have the real part half. In this case, I mean, that is a line parallel to y-axis. That's the critical line. In this critical line, all the non-trivial zeros are of the zeros function is there. But if you see that 8-page proof of Riemann's prime number theorem proof, and in the 4th page in the middle of the paper, he is writing, he has made an assumption, and then he proceeded. He wrote saying that if I give the proof, I will miss my track. Therefore, I postponed the proof. So that proof he has not supplied, and the people assumed it and then started doing many mathematical aspects. If anybody disproves this hypothesis, this assumption, then 75% of mathematics you have to throw it to Bay of Bengal. That is the status of Riemann's hypothesis. Thank God now that a lot of prizes are available for this Riemann hypothesis. That is why when Hilbert was interviewed by a newspaper man, he was asking one question, whether suppose you die and then God is giving a boon to you, when you coming out of your grave, what will you do? Then he was telling, I will ask the question, is Riemann hypothesis settled? So from 19th century to 20th century, we have been carrying over this. Even now, the problem is now trying to give the proof. There are many people going on trying, and this paper written by Professor Ishwaran, has been downloaded by more than 1,000 people, and it was referred to a committee. All these things are going on. Even you can see it in your Google. You can try to find out the paper written by Ishwaran. Why I am telling this? That is a challenge. There are so many challenging problems are available in mathematics. Okay. Now it is something like climbing Himalayas. Now mathematics is beautiful, like powers. Look at this formula. E raised to I pi equal to -1. E is one number, I is another number, pi is another number. They are all different religions. If all the religions are put together and it is giving the value -1, when you take that -1 left hand side, it's at the +1 equal to 0. So the 0, 1, you know the utility of 0, 1 in this digital era. So all the 5 elements are linked in this simple formula, Iris formula. This is the beautiful formula in mathematics, I can call it. What is the beauty? Beauty is defined like this: simplicity and depth, and that is equal to beauty. So beauty is defined to be the simplicity but having a long, a deep meaning in it. Here is another Euler formula. Vertices, number of edges and number of faces. This is equal to 0. Or platonic solids obey this formula wonderfully. So, like that, this mathematics becomes a beautiful one. Mathematics is pleasant. Look at this formula. The same zeta function, when you take 2, is summation 1 by n square, its value equal to pi square by 6. What about Z3? Z3 you got 1 by n cube, no answer. Whether even if we don't know whether it is rational or transcendental or any other number, we don't know. Zeta 4 you have an answer. Zeta 5 you don't have an answer. Zeta 6 you have an answer. Like that, for even number of values of S, you have an answer, but not for odd values. So this is one of the very beautiful formula. This is summation 1 by n square. All students studying sequential series, this series is very much studied by students or introduced in the class. Whether in algebra or in calculus, they will introduce. And the original proof given by Euler. And this this has played very vital role in that particular century. Try to giving the proof of this series. And when Euler has given a proof, that also you can find it in our Google pages. The original proof given by Euler, it is really very interesting. Of course, there are so many proofs are there. Why I am telling this, mathematics is beautiful and also it is very pleasant, like your Raymond's Jaiho music. Okay. Now look at this. Mathematics is confusing. Why it is confusing? A bat and a ball cost 150 in total. The bat costs 100 rupees more than the ball. How much does the ball cost? So a bat and the ball cost 150. Bat costs 100 rupees more than the ball. There are so many ways you can solve this simple problem, but the students will be confused by putting like this. People are afraid of reading mathematics, so they call it word problems. Word problems will always confuse you because they will play with words. The playing with the words will definitely lead to confusion. That is why mathematics is confusing, like walking in the dark. Mathematics is full of pitfalls. When you take any paper, high-level paper, people won't give the complete proof and they will jump. So mathematics sometimes it is filled with pitfalls. So you can see that if you try to give the proof, then you can get a very nice award for giving a proof for the gaps which are prevalent in some of the high-level papers. Therefore, ideas are because of the page restriction, they will not give all the details. And therefore, mathematics is with full of pitfalls. Sometimes it is uninteresting. People are there, and then early days now people are afraid to go to mathematics because of it is uninteresting. The people remove 1 from 10 means 1 from 10 means they will remove this part 1 and then they will put 0. So this is the type of thing which is going on in WhatsApp for quite some time. Even for this sin x, they will remove that n by n, and then sin will become 6. Like that, if people are mocked with all these type of uninteresting things that are coming into mathematics. Because very casually they will play with this, and like a student snoring in the class. Okay, now I ask you one thing. Suppose you are introduced to dy by dx. I will come to that, what is the dy by dx and other things. Suppose you don't have dy by dx in mathematics, the differential calculus. What will happen? There is no train, there is no bus, there is no aeroplane, there is no ship, nothing. All these things are manipulated and calculated and implemented using the simple concept, namely dy by dx. So how the dy by dx came into mathematics? 2 problems from Isaac Barrow. Isaac Barrow is nothing but Newton's teacher. he gave two problems to the students. Question 1, what is the tangent to the given curve? What is the area under the given curve from A to B? These are all the two questions. How to calculate a tangent to a curve at a point, and what is the area under the curve from A to B? I mean, x is going from A to B in the x-axis. So these two simple problems led to two different branches in mathematics. Namely, the question number 1 leads to differential calculus, and question number 2 leads to integral calculus. So these two problems given by the Isaac Barrow to Newton and his student and his colleagues, and the Newton came out with an answer, right? And later on, that dy by b, namely the derivative constant. The derivative constant at the same time was given by or introduced by even for integration Leibniz. So there is a lot of controversy between Newton and Leibniz. The matter was referred to London Mathematical Society, and then at that time Newton was the president. He appointed a committee to inquire about the contribution of Leibniz. Then people gave verdict saying that all these Leibniz results are nothing but Newton's result. Newton has got the priority, and except one thing which is escaped from Newton is differentiation under the integral sign. So that concept Newton has not done, whereas Leibniz has done. So these are all the historical prospects of mathematics. Okay. History of calculus. When you talk about the history of calculus, I told you it is starting from counting the sheep. So using pebbles, calculus. So the calculation is the word which means pebbles. And this history of calculus, it's a part of mathematics focused on limits, function, derivatives, integrals, infinite series, and sequences also. Known as infinitesimal calculus because I always introduce this concept to the students. Now we know from 3rd standard onwards, if 10 pencil cost 12 rupees, what is the cost of 1 pencil? This is 1 here, it means 1 unit. The same 1 unit, that is what in infinitesimal calculus also. If delta x is the small time, in that time it happens to be there is a variation between x and y. If there is a small variation in x denoted by delta x, small variation y is given by delta y. What will happen into the 1 unit of time or 1 unit of whatever it is? Delta y by delta x, like 12 rupees by 10. Like that, the same thing delta y by delta x. This is called the quotient, Newton quotient. And this Newton quotient, when delta x tends to 0, it is going to some number that is different with a different derivative. So these all these things are elementary that you know. That is called infinitesimal calculus. But the main idea comes from the 3rd standard mathematics. Namely, 10 items cost this much. What is the cost of the 1 item? When you ask this question, the same thing he can answer him. When you take the small variation, what will happen to the 1 unit of time or 1 unit of whatever it is? That is an infinitesimal calculus. And this constitutes a major part of the modern mathematics education. Of course, it has 2 different branches, differential calculus and integral calculus, which are related by, now the marriage between differential calculus and integral calculus is done by the fundamental theorem of calculus. Calculus is the study of change, whereas geometry is the study of shape. Algebra is the study of operations and their applications to solving equations. The course in calculus is a gateway to other science disciplines. More advanced courses in mathematics devoted to the study of functions and limits, broadly called mathematical analysis. Now we are slightly shifting. Under the name of mathematical analysis, all these things will come into the picture. Fine. Like that, now the Indians also has made a very tremendous contribution to calculus. Take it in the case of before Newton, we have the calculus given by Bhaskaracharya. So Bhaskaracharya, it is all everything in terms of words. So when you versus when you read it, then when you translate it into mathematical symbols, what is the nowadays you calling it calculus? It is done much before Newton, but the credit goes to only Newton, not Bhaskaracha. Okay, now this is a tragedy part of Indian contribution. Now, from this integral calculus, also the same thing. We started with the calculating area of. Actually, I introduced this integral calculus in a different way. For example, when you take a single point, what is the area of a single point? It is assumed to be 0. If you look at Earth from the moon, it will be like a point. So the area is 0. But when you go closer and closer, but it is the area. Right? When you take that square side with A square is the area. For rectangle A and B, AB is the area. When that circle or any regular polygon, so you can find out the area. But you have that x is equal to A and then x is equal to B. You mean x-axis. All the three sides are straight lines. Only thing is I am making this upper portion as the curve. What is the area under this curve? Between A to B. So instead of rectangle or square, I am making the top edge as a curve. So that is a starting point for the studying the area under the curve. So the integral calculus was nothing but what we have to do is a simple thing. So any unknown area, we have to calculate from the known area. We know the formula for rectangle. So that the area is divided into different pieces of rectangles and then adding all the rectangles and then you will get approximately the area under the curve, given curve. Or this is called the method of exhaustion, right? This is how mathematics, starting from the beginning, how it has been developed. When you see it, you will see that. Because from the known thing alone, you can understand how to calculate the unknown things. At around the same time, there was a great deal of work done by Japanese mathematicians and then Korean mathematicians, Japanese mathematicians, and European mathematicians. Now, look at the calculus. Now, what you are seeing is water drops and flying out of along the tangents to the edges of the umbrella. When you take that rain comes and then take the umbrella, when you rotate the umbrella, you can see that or the points, there will be so many points here, and these points, this will be tangent at that point. So that's what it water drops flying out of along the tangents of the edges of the umbrella. So this as she was introducing this, mathematics is coming out of natural thing. Exactly. Natural thing you observe perfectly, then you can give approximately, you can represent it by means of mathematical model and we can find out some interesting results. One thing result is this. Look at this umbrella. Nobody noticed this, but hereafter when rain comes, when you take the umbrella, just to rotate it, you will see the beauty of tangents, right? Tangents to the curve, but at this point. Now you can see the tangents as a water line. Okay. Now, and this line, and then when you put it mathematically like this, you can see that slope representing the instantaneous velocity at the point at time t. Okay. Now, limit of a function. You know, it is all started with the relations and then functions, neighborhoods, the limit of a function. These are all the development. You might have seen in our +2 class itself. What is the relation, what is the function, and what is the related neighborhood and the limit of a function. How very easily defining the function, but never accepted this concept of function in the early days. There are a lot of discussion, lot of disagreement over the concept of defining the function. Now we have a wonderful definition for a function as a mapping from one set to another set like this. And then when you take the limit of a function plus value of the function at the point, you can define the continuity like that. And then there is another definition, sequential definition. For example, when you take xn is a sequence of points on the real line, and then when you take the limit of this, it is going to point x. Then f of xn going to the value of f of x, then we say that function f is continuous. This is called a sequential definition. Earlier, what is the limit of the function plus the value of the function, both are same, then we say that the function is continuous at that point. Now here also continuous. The sequential definition, why we have the sequential definition, it is used in almost all in functional analysis. There they will define a transformation. The transformations are continuous, means they will use only sequential definition to establish the continuity of the transformation. And the next is this epsilon delta definition. It is a very, students hate this definition epsilon delta. When you put epsilon delta, people will run away from this classroom, right? And then how this epsilon delta, this introduction itself, Lebesgue, when he introduced this in his PhD thesis, nobody agreed his concept at that time. And then people started questioning so many questions. Because of that, Lebesgue could not get position in any university in the initial days. Then at one point of time, people recognized his contribution. I will come to that. What is his contribution? What is his way of thinking? So this is what we want from the young minds. Young minds, what you want to think. You have the concept, you have certain assumptions. What will happen if the assumption is dropped? What will happen if the assumption is modified? When you think like this, don't take it as such. You ask the question even on the assumptions. Of course, you have to take it granted, only for the examination point of view. But your mind should ask always questions, why we have to assume like this? What will happen if it is not assuming it? For example, now I tell you one thing, in geometry, there is a parallel axiom is there. What is the parallel axiom? Parallel lines meet at infinity, right? This, why you should ask the question, why you should meet at finite? Why it is not at finite point? That question led to another branch of mathematics. This is called hyperbolic geometry. That hyperbolic geometry, parallel lines meet at a finite point. So like that, when you modify the hypothesis or assumption, or when you extend it, you will get a new branch of mathematical activity. So this epsilon delta definition, it is nothing but you are talking about the limit. That the limit is whether you are imagining it or you are calculating it. Two things are there. Because now suppose L is the limit. That is a question, the defined limit of a function. Suppose, the word suppose is used. Suppose L is the limit of the function, then we will define limit extending to 0 or extending to some constant A, f of x is equal to L, then we say f is continuous at A. So this is how you are assuming the limit of the function, or you are surmising it. Or, sir, I don't want to surmise, but I want to say, I don't want to know that limit at all, but how to discuss this limit concept. That is where the Cauchy's definition comes. And this Cauchy's definition, you are using it in the numerical analysis. When you do it in the simulation, you are using this. All these things are possible or not, that's another question. Yes, it is possible on the real line because real line is complete. It's a complete space, topological structure. In complete, every Cauchy sequence converges. So the Cauchy sequence, I am taking n and n plus 1. Next one, not am and an. Next one I am taking. If that n and n plus 1th value less than some prescribed number, then we stop that iteration. Okay, these are all the Cauchy's idea or principle. It is used in the simulation, but nobody expresses. No book describes this. I mean, you should ask the question, sir, why we have to stop with this? With the prescribed or required accuracy, you are stopping that iteration process. How it is possible? Is it allowed? What property allows you to take this? What property it allows you, or in any judicial reason for this to stop this iteration business, right? In the simulation or in the calculation, in numerical integration or numerical differentiation, and you will study this only for the next 2 iterations less than some prescribed error, you stop it. So why I'm telling this epsilon delta definition, it is the backbone of all these things. Okay, now another way of defining the definition of continuity is left hand limit, right hand limit, and the value of the function. All the three are same. We say f is continuous. You know, left hand limit may not be equal to right hand limit. Then the function is not continuous. Both may be equal. Left hand limit, right hand limit may be equal, but the value, if it is not equal to the value of the function, then it is discontinuous. So this is a very nice idea that any +2 students or first year students can try different types of functions having left limit, not right hand limit, right hand limit with left hand limit, and value of the function. Or if all the three are equal, then only we can say that the function is continuous. And then this is higher level definition, but we don't teach in our engineering courses or anything. If you go for higher analysis, then you know that lower semi-continuous is equal to upper semi-continuous, that the function is said to be continuous. So, but what is the continuity definition you are mostly using is the definition 4 and definition 1. Other definitions, engineering students won't use it. I mean, occasionally you may use this definition 3. But definitely the definition 2 is not used in engineering, but it is used in application of functional analysis. Okay, this is about the continuity. Now look at this differentiability. Newton quotient I was telling about, if delta y is the change in delta x time, for 1 unit of time, the change is delta y by delta x. That's why it's a rate. We are asking the rate of the pen means, that means rate of the per unit. Here the per unit of time. That is why we are dividing by delta x. What is the basic assumption here is, when delta x tending to 0, delta y also tending to 0. So I mean both are tending to 0 when the delta x tending to 0. So that is you are getting 0 by 0 form, right? But at the same, this idea, when you want to extend it to set valued functions, you will get different types of branch in measure 2. Okay, that I don't want to tell you because it is above your level. Now the run over the race is nothing but dy by dx. That is the differential. But delta y by delta x is a quotient, but dy by dx is not a quotient. It's a number. It's a coefficient. That's why it's called a differential coefficient. So it is a misnomer. Like that in mathematics, there are so many things. When you write the summation symbol, what is it? Represents series or it represents the value. That's that. Because we understand when we use which place it means what. So this comes in practice. Then relation between continuity and differentiability. Differentiability implies continuity, but the converse is not true. These are all very standard things in mathematics. Now the rules of definition, you know, I just script this. There are so many rules are available, and here the nth derivative, first derivative, second derivative, third derivative. So many times you can derive the function. Up to that you get 0. Like that, this is the nth derivative of the product of the function u. That's a formula due to Leibniz. It is escaped from Newton. Now look at this primitive. Now, so far about a differential calculus, and because we started with the 2 problems, one gives the differential calculus, another one gives the integral calculus. Now here comes the integral calculus. What is it? When capital F of x is denoted by integral f of x dx, where f of x is equal to f dash of x. Now here you are actually, it's a differentiation is there and the integration is there in the definition. So this f of x, it's called a Newton integral or primitive integral. Now the word you might not have heard about this Newton integral, and now in the revised version of the +2 book, we call it Newton-Leibniz integral. There's a primitive integral. Now we have written it as Newton and Leibniz integral because we don't know which person has contributed first. So why should we lose the credit of Leibniz? So we'll simply call it Newton-Leibniz integral. That's what we have studied in +1 and +2 classes. When you come to engineering and other courses or undergraduate BSc and MSc, this integration concept varies slightly. Okay, right. What you are doing here is, given x-axis, as I told you, between A to B, you are integrating the function f of x. That means you want to calculate the area in between x is equal to and x is equal to b. Now what you do is, you sum the lower rectangles and upper integrals, upper sums, lower integral and upper integral. Sorry that I could not draw figure here. I need some other, let me see whether I can go for it.
No, sir. You come to the bottom of the PPT. There you will have that pen symbol.
What's it called?
You bring the cursor to the bottom of the slide, sir. You will get that pen. Come to the bottom left.
Bottom left.
Yeah. No, you are having it in PDF form. Sorry,
Yeah,
sir, that will work in PPT. Sorry, sir.
Oh, this is in PDF.
Okay, sir.
I can write it in PDF. For which I have to use different software. Actually. Right, because no, I want to give the classroom atmosphere. Therefore, I have taken this. Okay, now I tell you what it is. Actually, what you are doing here is between A to B, you are dividing that. First step is divide this A to B into partition. Once you write the partition, then you can construct the rectangles under the curve using the lower end point of the curve, and then upper end of the curve you will calculate the area which is bigger than the required area. But when you use these lower rectangles, you will get the sum of all the royal rectangles. You will get the area which is less than the given area. So this is how. And when the partition becomes more finer and finer means when you add more and more points, then upper sums will become very near to the exact value, and the lower sum will increase to the exact area of the curve. This is the idea of Darboux. So Darboux integral is nothing but lower integral and upper integral. Of course, now what is that partition in the y-axis? You take any point in between the subinterval. You take one partition of the x-axis. From that you take a point. You take the value f of t, and then you will calculate area, which will cover some area for the portion, and then it will leave some portion. So you are taking the middle sum. People are confusing in the textbooks between Riemann sum and the Darboux sum. The reason is, excuse me, just a minute. Somebody else will call. Sorry for the disturbance. Now that and then Riemann integral is different. So, but luckily, whatever the way you are getting that Riemann integral value and the Darboux integral value, both are same, and therefore people are defining in textbooks Darboux integral as Riemann integral. For example, when you take methods of real analysis by Goldberg, he defines Riemann integral, Darboux integral as Riemann integral. Actually, it should be different. Darboux integral concept is different. Riemann integral concept is different. Because this, the difference between Darboux integral and Riemann integral, as the undergraduate level, both are same, therefore do not bother about it, then you can excuse them. But when you come to PG, they will study Riemann-Stieltjes integral, where it makes the difference. It is not. Riemann-Stieltjes integral is not equal to Darboux-Stieltjes integral. Darboux-Stieltjes integral are announced or written, even the Rudin's book, also the Principles of Mathematical Analysis, he is writing Riemann-Stieltjes integral. Actually, that is Darboux-Stieltjes integral. Only that Riemann sum, when you use it, it is the Riemann-Stieltjes integral. Actually, this is the class of functions which are coming under this concept is a subclass of Darboux-Stieltjes integral. Okay, fine. Right now, what we have done in the, as I told you, basically you must shake the basic assumptions. You have taken an x-axis between A to B. You have taken the partition on the x-axis from A to B. But the question now, ask yourself, why? Why you want to take the partition on the x-axis? Now, Lebesgue thought about it in his PhD thesis. He has not taken the partition on the x-axis. He has taken the partition on the y-axis. A slight change. You think differently. That's all. A new branch of mathematics has come. Lebesgue measure, Lebesgue integral, all high in the high space integrals are based on a simple change. Why do you want to take the partition on the x-axis? I want to take the partition on the y-axis. That means in between f of a and f of b. When you take one point on the y-axis, you just draw the line wherever it cuts. Now you take the small interval in the y-axis. Now the small interval which cover some portion of the curve, corresponding excessive collectives. Corresponding excessive collectives. That is what we define as a measurable sense. That is the idea behind this Lebesgue integral and Lebesgue concept. Other things are very. Once you understand this basic concept, then the Lebesgue measure and the Lebesgue integral, even the measure theory will become a playing tool, a playing toy for you to understand this Lebesgue measure and the Lebesgue integral. Even measure theory will become a very easy object. Right. Now, a few areas that include mathematics is technical sciences like networking, computer science, software development, physical sciences including engineering, physics, and chemistry, social sciences like communications, linguistics, anthropology, economics, geography, education, etc. Medicine, life and health sciences including pharmacy, biology, optometry, psychology, and nursing, etc. Actuarial science used by insurance companies and business and commerce, they will use a lot of mathematics. And recently there is a branch called financial mathematics. And the financial mathematics, or when you want to know the engineering, financial engineering, they call it financial engineering also. And they use a lot of stochastic processor and integration and stochastic differentiation concepts. Now that in engineering point of view, where you are using the mathematics, suppose you are not having the mathematics idea, you are not going to be a very good engineer. That's what I'm going to show you now. Mathematics is used in every area, has its own functions and has many career options. Algebra is used to study symmetry in chemistry, networking, computer science, physics, and cryptology. Now, calculus is significant in biology, chemistry, hydrodynamics, physics, rocket science, engineering, option price modeling in economics and business, molecular structure, and then biomathematics. Right? Now, why mathematics for engineering? This is the very this is what that's the purpose of my today's lecture. Why mathematics for engineering? Because I think if AICT people also listen to my lecture, then they will revise the thinking of taking mathematics from engineering science. It is a grave danger for engineers when you reduce mathematics as well as physics, even chemistry. So they need it. Now the people are thinking of introducing biology also in the engineering, because this biology also engineering gives a lot of ideas. For example, when you look at the architecture of the temple architecture, it's based on our biology of our hand, how that and when you rotate it, how our bones are rotating here. This idea is used now without any paste. All pillars are standing there. How it is possible? What type of engineering they were used in the temple architecture? You will see that all the human body structure they have used in the construction of structural engineering. They will use only the human body ideas. So biology is also an inevitable subject for engineering development. This is about mathematics. Now we'll take branch by branch the role of mathematics in electrical engineering. Differential equations in mathematics and find importance in electrical engineering for solving circuit equations. There is another subject in electrical engineering related to electromagnetic theory, which involves mathematical concepts and calculus and building sound knowledge based on learning triple integrals. And then, in fact, when I was teaching that engineering mathematics, I used to give that triple integral where it is not usual cube. It is not usual thing. Because, of course, you have the surface, but here the x-axis and y-axis and z-axis, all the three are different values. Then how to calculate the value? There you need that I understand how to evaluate the three-dimensional integral. Okay. When mathematical linear algebra is interconnected with electrical engineering and the concept of circuit theory and the signal processing. Of course, the signal processing is a very another interesting aspect where not only here the algebra is used with the Fourier transform is also used there in the study of signal processing. For mathematics, you cannot. If you don't have a nail, your finger has no value at all. It will not do anything. It is useless for operating. Even you cannot lift things from. The role of mathematics in electrical engineering, students have an advantage over mathematics to grasp basic to advanced difficult concepts in core electrical engineering subject. In fact, in Indian science and it is that all engineering students are studying function analysis as one of the papers. But here in other universities, university education or colleges, engineering colleges are affiliated to any university or is what is called self-financing or other engineering institutes have their own way of conducting examination, their own way of grasping, framing syllabus. All these things are available. But when you look at the Indian social science, why the Indian social science is considered to be the topmost in India? Because they treat mathematics as part and parcel of engineering education. And learn about, in engineering students learn about all extensive use of Laplace and Fourier transform equations. I tell you, which is related to linear algebra, circuit theory, and signal processing. Okay. What about the Laplace transform and the Fourier transform? For example, to explain to a common man, see, when things are spread over, or you take a box full of chalk piece. When the chalk piece is spread over, what is the use? We want to put it in a box. That putting into the box, is there any mathematical construction for this? Yes. Your power series construction is nothing but all the discrete things you want to put it in contained in a box. For example, you take sigma x to the power of n, where mod x is less than 1. Its value is 1 by 1 minus x, and mod x is less than 1. So 1 by 1 minus x is the function. So this is called boxing, or discrete quantities are putting into a function, namely 1 by 1 minus x. Same thing with the Fourier sense. Fourier transform is something like, for example, now, sir, if the discrete things, you can put it in a box. What about the liquid things? For example, now you cannot put that ocean in your bottle, but a glass of water, you can put it in a bottle. So that is nothing but your Laplace transform. A continuous function, a continuum of material that you can pack it through bottles. That is the Laplace transform. Laplace transform is also a packing mechanism of continuum of points. But whereas the power series are generating functions are nothing but packing your discrete things put together. If you take the basket full of apples, that is, basket full of apples is nothing but the generating function. If you take a Coca-Cola bottle, means it is a Laplace transform. This is how you have to remember. What is the Laplace transform, what is the Fourier transform, and what is generating function. The mathematical complex number algebra find maximum user solutions of sinusoidal excited circuit. So these are all, when you go to that other classes. Okay, now coming to the electronics engineering, numerical methods, and then software algorithms and matrix algebra, or you can say that significance of mathematics and science is equivalent to being mother of all sciences. That's why it is called the mother of all sciences. Why mathematics is important in electronics engineering? In electronics engineering, there is a requirement to understand the typical concept and expand the knowledge to understand various mathematical concepts based on differential calculus, integral calculus, and complex numbers. Okay, where they are using it. I will come to the next slide. In every branch, how mathematics is used. That I will go to that side. Topic wise. Yes. For example, now you take a mechanical and civil engineering, fluid flows. When you want to study fluid flow and the stress analysis, you need to have a mathematics. Sports and exercise engineering, biomedical engineering, signal processing and analysis, and power meters and heart rate monitors. All these things are mathematics. energy systems engineering, design of control systems to protect ocean energy converters at sea, civil engineering, traffic engineering and modeling, structural engineering, all these things, background is mathematics. Then electronics engineering 90, computer graphics, zooming, now rotation, transformation, animation, and digital communication. How this is possible? When I am sitting in one room, I'm shouting as if I'm a mad man and talking only by just looking at my laptop, right? Nobody is there, no student is here, but I'm talking, but you are listening to me. You are seeing my picture. How this is all possible? These are all possible because of background of dedicated mathematics designed and used by the engineers, very good engineers. Then let them take the electrical engineering, AC circuits, then engineering application to mechanical engineering, resolving forces in a plane, design keys and design of aeroplane landing gears. Look at this. I will give one beautiful example of an aerospace engineering, how mathematics was used. Civil engineering, structural engineering, surveying, traffic engineering, geotechnical. Right. Now, in electrical and electronic engineering, oscillating waves, circuit, signal processing, electrical and magnetic fields, design of power generating inputs, radio frequency, system and antenna design. So, where? You cannot just put that antenna and then put it there. That is a calculation. That is a typical mathematics behind it. Energy systems engineering, design of sun tracking mirrors, stars and concentrating solar power plants. Okay, aeronautics. Now look at this point. Boeing 777 200 fighter plane tails strike at the Copenhagen airport in 2011. It happened. Changes were made to landing gear design and new computer algorithms developed to prevent pilots increasing pitch if there is a risk of tail strike. How this aerospace engineering, how mathematics is used to avoid the tail hitting the ground. So everywhere, I mean, when you then after listening to this lecture, you will see that you can see only mathematics, not engineering. Engineers are only using that mathematics to have a very good output. That is why we changed from Bachelor of Engineering to Bachelor of Technology, BTech. BTech means you are bringing the engineering concept to the public, to the use. But BE means you are studying and you are forgetting and you are going away. But whereas BTech means, technology means you are bringing these engineering concepts to the public use. This is the explanation given by Professor Mathematicians of former Vice Chancellor. Now he is no more. In one of the meetings that I attended, he explained what is the difference between engineering and technology. So there he explained this. What is the engineering concept? What is the technology concept? It's not my explanation. Now this algebra is used, computer science, cryptology, scheduling tasks, alteration of pattern pieces of precise name. Now all these things are coming from by just listening the pattern recognition of certain things they are happening in nature. Then you analyze the pattern and then you apply some mathematics to that. Then you will get a very nice, beautiful output. Differential equation, I did not tell you. The part and parcel of engineering mathematics is ordinary and the partial differential equation. Of course, Fourier analysis also. In fact, when I was giving lecture in some other forum, signal processing, how Fourier transform it is used, that I explained in one lecture covering so many aspects. How the Fourier transform or Fourier analysis of information image processing techniques. How mathematics is used in image processing techniques. Okay, most of the physics and engineering, sound waves in air, crystal growth, cyclical modeling, casting of materials, material science, electromagnetic, etc. These are all the applications of differential equations. Now, I have listed out so many things, but anyhow, you just understand that mathematics will play a role in each and every aspect of engineering what you are studying all the 4 years. In fact, we used to have M1, M2, M3, M4 also. Now it is reduced to M3 only, right? Only 3 papers you are studying it. But earlier, I remember in Annamalai University, still the classrooms are called M1 classroom, M2 classroom, and M3 classroom, and M4 classroom, because they are mathematics for engineering students being taught there. Okay, now I think another thing, probability and statistics is it's a modern technique. Remember, I tell you one incident. One ship submerged in a ocean. They could not find out where it was. But using that Bayesian idea, Bayesian inference, they could locate that ship and then they got taken it out. This happened near Japan. So the probability and statistics is another branch which is also useful in analyzing certain data items. Right? Fine. And numerical analysis I need not tell, because why numerical analysis? For example, if anybody asks where is LIC in the Mount Road, they may not know. But the old building, Spencer Plaza, is known to everybody. So near Spencer Plaza, there is a LIC building. So you are not able to calculate exact value for any equation or differential equation or partial differential equation. At least the nearest value you can calculate. That is the numerical analysis. And this numerical analysis, that is what I was telling in the beginning. You are doing that numerical iteration, and the two iterations are less than the given error. You are stopping the iteration, because otherwise you have to continue. Exactly. But at some point you have to stop it. How to stop it? There the mathematics behind that will allow you, and the judicial reason behind it to stop the algorithm or the numerical analysis technique or simulation technique. It's all guaranteed by mathematical ideas. Right. I think another branch is operations research and optimization. And this operations research, linear programming, dynamic programming, nonlinear programming, and then queues, inventory, reliability, all these things are coming under broad topic called mathematical programming. But operations research is nothing but queues, inventories, and reliability. But people are confusing with the operations research with mathematical programming. These two are different. Mathematical programming is different. There you are talking about only algorithms and then how to get the solution. But whereas operations research is different, right? There you got the physical situation or social model, for which you have a mathematical model, and these mathematical model you are writing it in terms of mathematical equations, and these equations are solved using generating function or Laplace transform or combining both, and you will get the solution. See, this is how operational techniques are mostly followed. Okay, and this optimization, of course, I mean, it is the cousin of mathematical programming, right? I think there are so many topics are available under which you are using that OR and optimization techniques, right? Is there any wonders in mathematics? You are talking about the wonders in the world events. Now I tell you some of the wonders in mathematics. E equal to mc square. It is a wonder one. You can make electricity and sadly also bombs using this formula. A simple formula which you can destroy it or which can use it for the public. So this is a very dangerous formula as well as it is the wonderful formula. And wonder two, F equal to ma, force and acceleration. How they are made. Bodies move around in this universe because of this equation. Force and acceleration and the mass. And then third wonder is F G inverse square law, gravitational force. Earth goes around the sun because of this equation. How people thought about it. That is why they observe the nature and bring it to mathematics. Now, Earth goes around the sun because of this. And gravitational force, mass 1, mass 2, distance between them are square. That's called inverse square. Then wonder 4, black hole entropy. This black hole entropy is a probable infinitesimal volume and infinitesimal mass of the universe. This is going to give you an approximate value for volume as well as the mass of the universe. Now here, information entropy. This is really marvelous. The simple marvelous. For example, now you might have heard about 32-bit computer and 64-bit computer. What they are, how they are determined. Sir, suppose I want to send a message to my friend 0 to 7, 8 numbers, 0 to 7. What I have to do? What type of computer I have to make in order to send 0 to 7? In order to send 0 to 7, see this Pn is nothing but the probability. 1 by there are 8 numbers, the probability is 1 by 8. So all are equal. P1, P2, P3, P8, P7 up to P7, it is equal to 1 by 8. So 1 by 8, log 1 by 8, log 1 by 8. That means 2 to the power of minus 3. Then here it is, here it is a 2 cube, because there is 1 by 8. 1 by 8 you can write the 2 into 2 into 2 to 2 cube. Now here it is a 2 to the power of minus 3. Then you can get this value, the minus minus will get cancelled. You will get log 2 with base 2 equal to 1. Then you will get only 3. Sum is equal to 8. 8 will get cancelled because the 8 items are summed up. 1 by 8. Therefore, you simply have log Pn. So this log Pn is nothing but 1 by 8. 1 by 8 is nothing but log 2 to the power of minus 3. Minus 3 and here minus 3 is there. Therefore, it becomes plus 3. Therefore, I need a computer with 3 bits to send a message 0 to 7. Look at this. That is the information. That is what you have in the digital era. Digital era use this information entropy. This information entropy, it is a measure of the communication, measure of the information. So the measure of the information, when how you are going to measure the information of sending 0 to 7 to other person, you need a 3-bit computer to send the message. So like that you have the 32-bit and 64-bit computer, which is based on what you want to transact, what type of information you want to analyze. That is wonder 5. Then wonder 6, it is wonder Maxwell equation. This is 3 and 4, it is due to Gauss. First 2 is due to Maxwell. It's called the Gauss-Maxwell equations. The rhythm behind the cosmic dance. Lord Nataraja of Chidambaram is performing all these 4 equations, and the whole universe is moving. With the movement of Lord Shiva, it is given by this Gauss-Maxwell equation, and this represents the cosmic dance of Lord Nataraja, for which these 4 equations are there. Is that wonderful? 7. This is Schrodinger equation. The rule of God's game of dice is this. Now here again, there are so many open problems are available. 3-dimensional Schrodinger equation is yet to be solved. It's an open problem. How wonderfully I started with e power I pi, I am ending with e power I pi. Already I told you this is a beautiful equation in mathematics. This Euler formula, inanimate symbols of different genesis. E is one variety, I is an imaginary unit, and then pi is another transcendental number. So all the 3 religions are put together, giving -1, or rather you put shift it to left hand side, become +1 and 0. 0, 1, and these 3 symbols. The three symbols, E, I, pi. This value is how it is coming to -1. And then when you add it to the -1, it becomes 0. That is wonderful. That is why it is a beautiful, simple formula, but it has a deep meaning in it, and that is depend to be the beauty of mathematics. Okay, students, I am going to give you, because today's lecture you should learn something new. I am going to give you a tool, or I am going to give you a trick which is not available in your usual textbook, or you might not have studied in your +1, +2 class, or your engineering course anywhere. Now I am going to give you one. Teachers also can take note of it, and if you want, you can repeat it in the class. Namely, Feynman method of differentiation. And the Feynman method of differentiation is, suppose a function is given u to the power of a, u to the power of b, and u to the power of c, then Feynman differentiation gives the formula f dash, that is equal to the same function f, the power equal to a, and then u dash by u plus b, b dash by b plus c, w dash by w. This is a, you can say that if f equal to e power a, then you can find out logarithmic differentiation. This is another version of logarithmic differentiation. But in one stroke, you will get the answer. That is the beauty of this Feynman differentiation. This is not included even in +2 or engineering or any book on calculus. This formula can be taught to the students, right? Feynman is a very good physicist. He has his own way of thinking. His method is very wonderful. He's in the differentiation. Now look at this example. Now when you really, when you your mind will become rough when you read this, how to differentiate this. You go sine cube. Here the square root e power x square, x square plus 1 by 3. But Feynman has given a very beautiful formula. Now you go sine x, then this is an one factor and this is another. There are three functions are there. So u equal to sine x, but u power a is a equal to 3. B equal to e power x and x square, b equal to half because the square root. And then w equal to x square plus 1, but c equal to minus 1 by 3. That's all. Now we write f over again, df by x. The same f is repeated here, multiplied by that a into du by dx and then b into dv by dx like this. Add b, then finally you will get now you see the function, original function, multiplied by 3 into u dash divided by u. Sin x differentiation is cos x. 1 by 2 is the power, and then here e power x, e power minus x, e power x into 1 plus 2x. That differentiation of v and dv by dx. What is c equal to minus of, and then you get this 1 minus 1 by 3, and then differentiation of this. This is the way. In one step, you can write down the answer. Now, lastly, Feynman integration method. This Feynman integration method, sometimes it will be very useful in a very complicated integrals. Even for example, integration sin x by x, when you use Feynman method, in few steps you will get the answer without complex analysis. Now, the first step is introduce a parameter alpha so that the integral I becomes a function of alpha, I of alpha. Given I, it becomes I of alpha. Compute the integral I of alpha for particular value of alpha, which gives 0. That is like I of 1 equal to 0. Say, not necessarily. For any value when you substitute for alpha, it should given to 0. Okay, now differentiate the integral with respect to alpha. You have introduced the parameter. Do you know what is meant by parameter? Parameter is nothing but it does the value of both variable and constant. That's why it is called a parameter. Parameter does the value of both. Now, you treating this as a variable, now differentiate with respect to alpha. Find I dash alpha. Then compute the definite integral with respect to x. Integrate indefinite integral with respect to alpha. Then you have f1 equal to 0 to compute the value of the remaining integral. Now I will explain by means of an example. Now look at this integral 0 to 1 x square minus 1 by log x dx. What you have to do? First of all, you have to introduce alpha. How we can introduce alpha here? When I put alpha x to the power of alpha, here x square is here, x to the power of alpha minus 1. When you put alpha equal to 0, anything power 0 equal to 1, 1 minus 1 equal to 0. Therefore, I of 0 equal to 0. So I introduced alpha. The second step I am checking for which value of alpha this integral, the integral becomes 0. So I of 0 equal to 0. Now differentiate this integral with respect to alpha. Now how this differentiation with respect to alpha, you are treating this alpha as a parameter and your differentiation is taken inside the integral for which this integrand satisfies all the necessary conditions to carry out the differentiation under the integral sign. Dou by dou alpha, when you are doing this equation, you will get x to the power of alpha dx. Okay, now I dash of alpha is 0 to 1 x of alpha alpha. Now step 4, integration with respect to x. Now remember, first you have to introduce alpha, differentiate with respect to alpha, now integrate with respect to x. Because here you are getting the integral 0 to 1 x of alpha dx. Now when you integrate it 1 by alpha plus 1. Now Again integrate, because you have differentiated with respect to alpha, you know. Now integrate with respect to alpha, you get log alpha plus 1 plus c. But I have 0 equal to 0, therefore this gives c equal to 0. So now alpha value in the problem given to be 2. So now introduce that alpha equal to 2, log 2 plus 1, log 3 is the answer. So, but the usual method when you apply it will take time. But whereas Feynman integral will give you answer very nicely. I hope today's lecture giving various applications and the usefulness of mathematics and various disciplines of mathematics. Just I have indicated only what are the different topics in which mathematics is heavily used, and the things which I want to introduce is the concept or idea which are not taught in our any of these classes so far. One is, or you can Google it, you will get the Feynman method of differentiation, Feynman method of integration. Thank you very much. Thank you for your active listening. I hope.
Thank you, sir. Thank you, sir.
I have not taken much time.
That's okay.
Yeah.
Thank you, sir, for enhancing and enlightening the young minds of our future engineers. Gratitude is the fairest blossom which springs from the soil. I'm glad to invite Dr. C.K. Shivashankari to propose the vote of thanks.
Good evening to one and all present here. It gives me immense pleasure to propose the vote of thanks. Gratitude is the mother of all virtues. At the outset, I take this opportunity to express the gratitude to our management for their support and motivation for all our endeavors. Indeed, it's great honor to extend my gratitude to our chief guest, Dr. S. Thangaraj sir, retired as Director and Head Ramanujam Institute for Advanced Study in Mathematics. Thank you, sir, for your thought-provoking and informative speech. And I would like to thank our respected principal for his guidance and moral support. I'm glad to extend my thanks to our beloved HOD of the department, Dr. S. Pave Madheshwari ma'am, for initiating webinar series in sciences which made students to acquire knowledge from all the aspects. I would like to thank branch coordinators for encouraging students in such participation and all the faculty members for the efforts taken towards making this event a grand success. Last but not the least, I would like to thank our dear students